Hello, everybody. Welcome. Welcome to PyData, Amsterdam. My name is Peter, and together with my colleague Diedrich, we're going to be hosting this session for you. First of all, congratulations for actually finding your way to this room. I know it's not the easiest task. I was struggling yesterday. For those of you a bit unfamiliar with the format, we're going to have 3 presentations from 4 different speakers. And at the end of the presentation, there will be a little Q&A session. If there's anything you want to ask, deepen your knowledge, make sure to ask. You will be picking the questions from the audience. And I think we can start. Our first speaker is Shimanto Rahman. He is a PhD student from Ghent University. He's studying machine learning and specializing in adapting these algorithms to meet specific business needs and business requirements. So please give a round of applause for him.
Yeah, welcome everybody. I'm so honored to be able to speak to you today. Thank you for the introduction as well. So yeah, I'm a PhD student from Ghent University. I'm also associated with the Flanders Make initiative, which is just essentially a way of bringing together industry with academics and doing some projects together. And today I'm gonna talk about cost-sensitive learning. Maybe before we start, are there any people that have never done any cost-sensitive learning, haven't really done anything? Maybe a show of hands? Yeah, a couple of people? Yeah, okay. Be ready to be gravely disappointed, but no. There's definitely a lot of good stuff in cost-sensitive learning. There's been a lot of advancements throughout the recent years that really haven't gotten towards the broader public. And one of the reasons is because of the software implementations of the researchers. Well, they were kind of scattered all over the place, and they weren't really accessible in pip installable packages. They were scattered across Python, R. Not everything was well documented. And that got me a bit frustrated, especially when I started my PhD. I started aggregating everything, and then I saw that maybe these methods could be useful for other people, like some of my colleagues and some of my students I was supervising. So I thought, well, maybe I should just make this an initiative and make it open source completely. So that's why I'm here today, to kind of present how you can do cost-sensitive learning in Python. The idea of Empulse, which is the package, is if you start from Scikit-Learn, you should only really learn some of the fundamental techniques and ideas, and you should be able to do cost-sensitive learning. And those fundamentals, if you don't have those already, I'm going to try and teach you. So I have 3 objectives today. The first objective is to kind of explain why cost-sensitive learning, what it is, why it's important, and maybe why some of the traditional machine learning is always up to the task. Then I'm also going to try and teach you those fundamentals. So what is a cost matrix? How does a cost matrix translate to a metric? And once you have this metric, what do you do with this? And third, I'm going to show you how to implement this in Python. I'm going to start with what you can already do with Scikit-Learn, and then I'm also going to show you how you can kind of supplement this with the Empulse package that I've made. So let's start. What is cost-sensitive learning? The core idea comes down to this. Classification mistakes are not made equal. I think it's best to show that with an example. Let's say you work for a bank, and there's a bunch of transactions coming in every day, and you're interested in classifying, is this a legitimate transaction, or is this transaction fraudulent? So there's 2 mistakes you can make. The first mistake is, you can say that a legitimate transaction is fraudulent, and you might block that transaction. The customer is inconvenienced. They might have to call the support. That also has some costs associated with it to unblock their card. You might lose some goodwill from the customer. They might not change banks later down the line if that happens too much. But the other mistake you can make is, letting a potentially fraudulent transaction go through. And that is potentially very costly. So you're kind of working with these 2 kind of mistakes you can make, but they're not equally weighted. And cost-sensitive learning, in a sense, is a way of dealing with this. How do you balance your model decision-making with these real-life constraints? Another example, in a completely different field, could be in medical diagnoses. Let's say you want to help a doctor make a diagnosis based on some medical imaging. You want to classify, based on this medical imaging, does person A, patient A, have this illness or not? Well, you can say to a healthy patient, well, you have the disease. This causes unnecessary anxiety, might cause extra tests, might give them some medication which is harmful for them. But the other case, could be potentially lethal, where you miss someone that is actually ill, and you might spot the illness way down the line, and the treatments are maybe more invasive and potentially lethal. So again, unbalanced incentives, like mistakes, and how to deal with that is kind of what cost-sensitive learning is all about. Now, last example I'm going to give is one for credit scoring. Let's say you have a data set. This is just like a German credit data set from OpenML. And you want to classify whether someone has good or bad credit. And in this hypothetical example, we're going to say that based on this, you're going to either grant someone a loan or not grant them a loan. Because you think someone with bad credit is not going to pay back the full loan amount, and you're going to lose a lot of money. We load in a data set, you get your X and your Y, you train, test, split, nothing, out of the ordinary at this point. But, so you do your usual thing, you build a couple of models, so logistic regression, random forest, like GBM, whatever you want, and you evaluate on some metrics. Accuracy, precision, recall, F1 score, whatever your preferred metric is. But you see, there's kind of a trade-off. One model is very high precision, the other one has a bit of a balance between the two, and the other one is very high in recall. Which one of those do you choose? Well, depends on your business situation or whatever situation you're in. How do you balance the trade-off? Well, if I give you some more information about this hypothetical business case, say, granting a loan to someone that has bad credit, on average, loses you about 5,000 euros, because they don't pay back the full loan. But granting a loan to someone with good credit, well, you lose out on the return on investment that you could have gotten, about 1,000 euros. Now, we can imagine that with this extra information, we can evaluate these models based on the real-life impact they would have. If we were to deploy this model would cost us this much because of the mistakes it made. And now we have a much more objective way of telling, of evaluating your models based on, this KPI that really interests you for your business or whatever situation you're in. So how do we get there? Well, what we need is the concept of a cost matrix. And the only thing a cost matrix is just a confusion matrix where you map every element of the confusion matrix to the consequence of that action, of that prediction in practice. So in this case, we're going to say that making a false positive mistake has a 1,000 euros cost, and a false negative mistake has a 5,000 euros cost. In this example, we don't associate any cost with it making good predictions, true positive, true negatives, but just know that you could also play with that if you want to. And then, once we have this cost matrix defined, then we plug this into this cost function, and then out comes the business impact of our model. And in practice, like building this cost matrix is probably the most intensive part, because this is quite an easy example, but this can very quickly become very complex, and really getting this business metric as close to as possible to the actual thing that you want to optimize in your setting is the main task. Okay, so how do we compute this cost metric? I've kind of abstracted it until this point. Well, it's actually quite easy to implement, at least this one. You just get your confusion matrix, you define your cost matrix, and then you multiply them elements-wise, and then sum everything together. Of course, this you don't have to do yourself in Empulse. Like, these functions are already defined for you, so you can already just import it and use it. There's also a bunch of other features in these functions that make things easier for you down the line. But So yeah, now we have a way of evaluating our models based on this KPI that we have defined. But we have made an implicit assumption. One assumption that we made is essentially saying that every customer is the same. Every person with good credits, if we get it wrong, loses us 1,000 euros. Every person with bad credit, if we get it wrong, loses us 5,000 euros. This might be an okay assumption to make if the ranges between the customer values are relatively similar. But if this is a bit more spread, where you have very high-value customers, very low-value customers, and anything in between, this assumption might not hold very well. So what we can do is move from these class-dependent costs, where every instance of a class has the same cost, to these instance-dependent costs, where every instance of a class has its own individual value associated with them. In this case, we can just make it very simply that, for the false positives, we just say it's the loan amount times the return on investment we get. But of course, this can be as complex as we want it. And for the false negatives, you just say, on average, we lose this percentage of the loan amount if this person defaults. Again, you can make this as complex as you want, but and then we can just implement that in our code, right? Same function, just instead of passing a single value, we pass an array of values, which indicates the cost for every single prediction instance. Okay, and then we get a bit, slightly more accurate representation of what the actual impact is of our metric, of our model. So we have now built a business KPI, a business metric that we can use to evaluate our models in. But wouldn't it be nice if we could, right now we're just building a model and essentially just evaluating it post hoc, right? We're building it, and that model has no idea of what these costs are. You're only evaluating it later down the line. Wouldn't it be nice if we can kind of trick the model into taking these costs into account directly? Well, turns out we can quite easily do that in Scikit-Learn. We just use sample weights, right? We use these costs as a sample weights for our model, and then we just plug it into the fit method like you've probably already done before. Nothing special there. And generally, this will lead to better results. But what if we don't need to trick the model? Because what we've done in the sample weight example is essentially just, we're still using the original loss function of the model, but we're kind of, weighting it a little bit. But in an ideal world, we could take this cost metric that we have defined and use it directly into our model and optimize that. Well, it turns out you can. There's in Empulse several models. This is, for example, the CS Boost, this cost-sensitive boosting, gradient boosting algorithm, and in there you can use XGBoost, SCADBoost, LightGBM, whatever you want. And that will optimize this cost directly. And instead of passing the sample weights to the fit method, you directly pass your costs, your elements of your cost matrix in there. And then you do your normal thing you would expect from a classifier, and then again you can evaluate it. So in general, in Empulse, there's a bunch of classifiers that are essentially translated to their cost-sensitive counterparts. So we have logistic regression, histogram gradient boosting, decision trees, random forest, and bagging. And from using this package, you don't really have to know how these models individually optimize this cost loss. Like, you don't have to know how the gradient is computed for the beta coefficients of a logistic regression, or how the impurity measure is done, computed to split the trees of the nodes of a decision tree. All of that is abstracted away. The only thing you need to do is define how your cost matrix looks like. One thing. So I've plotted, so Empulse is built on a lot of contributions that came before Empulse. A lot of academics that put their code online, a lot of other people that put their code online. So I'm very grateful for that, because otherwise it wouldn't have been possible. And I think one of the biggest contributors before was this costcla. This stands for cost classification package before, and it was actually also PyData speaker several years ago, I think 5, 6 years ago or something. By now, this person is like senior global director at ABN Bev, so they're not maintaining open source anymore. But at that time, a lot of the methods that were developed, in my opinion, were very targeted towards academics. They were not very scalable. Were nice to make a paper from, but if you actually wanted to use it in practice, because right now, what I've done, this is the execution time of the method before, I've moved a lot of the performance critical parts to Scikit-Learn. If you're not aware what Python is, it's just a way of essentially writing Python-esque code and compiling it down to C or C++, and then using that, which is typically a lot faster. I've used a lot of the backend that Scikit-Learn provides for making decision trees and other things for other models. And we're leveraging that to make it a lot faster. Because with this implementation, you can essentially make a random forest model of 100 trees at the same time you've made one tree before. So, this is the most extreme example, but there's other performance improvements that generally making these cost-sensitive models from something that's academically interesting to actually practically useful. So, recap. I've thrown a lot of information at you at this point. So let's kind of take a step back and think what we've done. So we've defined a cost matrix, which just tries to quantify what the consequences are of making a certain prediction. Then those can either be class dependent, where every instance of a class has the same value, which is fine if there's not a lot of difference between the instances, or it can be instance dependent, where every instance of a class has a different value, and that can be interesting when things are very spread apart. Then we've translated that to a certain metric, cost, profits, well-being of a patient in a medical setting or something like that. I've shown you the expected cost, but there's many different metrics out there. I'm going to go over some of them later as well. And now we can use that in different ways. You can apply it in, for example, model selection, which I showed you in the beginning, where you just build a couple of models and then just evaluating post hoc. You can also integrate them in the model loss, like I've showed you, like the different cost-sensitive model options. And then there's other options as well that out there, like you can do some pre-processing, like undersample or oversampling based on this cost to have the optimal ratio, or maybe tune the threshold of your classifier as best as possible. So when should you consider a probability to be 1? When should it be classified as 0? All these different methods exist and are available in the package. I'm not going to be able to go over all of them, but if you kind of peruse the documentation, you can find those. So one of the other metrics that I kind of tease you about is the savings. And that is particularly useful if you want to compare what your model is doing against a certain baseline. Because essentially what this is just it's taking the cost from the model you have trained, and then dividing that by the cost of a certain baseline. Let's say an example of the bad credit, good credit. Say that the bank said any loan above 10,000 euros we're not going to grant. It's too risky for us. That is our baseline solution because that was what we were doing before. Well, you can just simulate that by having this wide prediction of the baseline, saying any loan above 10,000 euros is automatically a 0. And we're comparing that, and we can see that actually there's a 35% savings over our model is saving 35% against this baseline. But this baseline can be anything. It can be a very naive model, can be a linear model, another model that you have in production, or whatever. Another example of a different metric is something called the maximum profit. And that is coming from a field. It's called profit-driven learning, which is kind of adjacent, like a sister-brother relationship with cost-sensitive learning. There's a couple of differences why things that come from that field might be interesting in your use case. The biggest difference is mostly like a semantic one. Instead of like minimizing the cost, you're maximizing profits typically, but that is really not that important. But you have like a cost-benefit matrix instead of a cost matrix where the good predictions have a benefit associated with them and the bad predictions have a cost associated with them. And then you have this maximum profit function that you define. So what is the biggest difference? So what we've done so far, right, in this cost-sensitive example, is we essentially looked at the individual predictions, 0, 1, or 70%, 30%, whatever, and then we've weighted that with the outcome that could generate. So an outcome of 5,000, 1,000, 0 if it's a good prediction. But what the maximum profits function will do is kind of, instead of looking at the individual predictions, look at the global predictions. We're going to aggregate with the true positive rate and false positive rate, and looking at the aggregate performance of the model. Now, before I confuse you even further, this is kind of like AUC, and I'm going to maybe kind of first explain what kind of the problem is with using AUC, of like a practical problem, and why maximum profit might be useful for you. So, if you've done any, like, if you've ever done something with AUC, you might have come across this curve. This is an RSE curve where you're plotting the false positive rate and the true positive rate against each other. And essentially what you're doing for different thresholds of your classifier, you're evaluating them on the false positive and false negative rates. And by itself, the AUC just calculates the area under that curve, and that's in general an idea of how good your model ranks things compared to each other. But if you ask a question, well, what should my threshold be? Well, when should something be considered a positive or a negative? This doesn't really answer. AUC doesn't really answer that question. We couldn't, make some intelligent decisions because, well, for example, if you compare the threshold of 0.53, we can see that the threshold of 0.54 is objectively better. For the same true positive rate, we have a lower false positive rate. So that is just better than that one. We can do the same for 0.39. You can see for the same false positive rate, the 0.38 threshold has a high true positive rates. And generally, we can do this exercise across this curve. And if we connect all of those, we can see that there's a bunch of different thresholds that could potentially be the optimal solution. But without any further information, we don't know which one of these thresholds is actually the best one. And AUC, again, doesn't really provide you a framework for that. But what the maximum profit will do is essentially evaluate your model based on these different thresholds and tell you where your profit is maximized. But again, I'm talking about profit, but this can be anything like well-being of a patient or whatever that you're maximizing. So maximum profit will tell you this threshold is the one you should use. And then evaluate the profit at that. Okay. So what I've showed you right now is what I call the direct API, where you just define what your cost of the false positives and false negatives and so on are directly, and just pass those to the methods, the models and the metrics and so on. There's also something called this metric API, which provides a lot of more flexibility when things become a bit more complex. So if you're happy with just using the direct API, make sure to just use that. But for some more flexibility, I'm going to show you what the metric API can do for you. So for that, I'm going to take an example. Another example of customer churn. Let's say you're a Netflix or like a telecom company, and you want to predict which one of your customers are going to cancel their subscription next year. And if you know this person is going to cancel, you might provide them with an incentive to just stay with you. Maybe you give them a better rate for the contract for next year. So what your model can do is two things. right? First, it can either classify someone as a churner, or it can classify someone as, well, they're not going to churn. For the ones that are not going to churn, you're not going to do anything, so we kind of can ignore those for now. But for the ones that you classify as churners, there's two things that can happen. First thing is they were actually going to churn, right? So you made the right decision, the right classification, or they weren't going to churn, so you made a mistake. We think at this point all of them are going to churn, so we're going to provide them an incentive. We're going to contact them. In the case of Netflix, maybe contacting them is not that expensive, but for example, if you're like in a B2B setting where you have sales reps and you actually need to drive there and set up a meeting, the contact cost is a bit higher. And we're going to offer them an incentive to stay. We're going to say that a fraction of the actual churners are going to accept our incentive. And for those, they flow back to our customer base, and we get the value of that customer, how much profit they are going to generate. But we lose the incentive cost, the reduced rates on their contracts and the contact costs that are associated with them. But there's also like a fraction we say that they're going to churn anyway. Whether we offer them an incentive, they're going to leave. They don't want to renew their subscription. They don't have any shows on Netflix they want to watch anymore. For them, you still contact them, but they don't go onto the incentive. And then for the non-churners, well, you think they're going to churn, so you offer them the same incentive, but no, they were going to stay anyway, so yeah, I'll take the better rates. Of course, why not, right? So we don't gain anything. So there's a kind of visual representation of a cost matrix, cost-benefit matrix. So how do we actually translate that to code? So I'm going to use a package called SymPy. If you're not familiar with it, it's a very powerful language to kind of do symbolic mathematics in Python. And the reason why I use this is down the hood, a lot of computations are happening, but for a declarative, for a user, you don't really need to worry about that. But know that down the hood, this allows me to do a lot of optimization. But what we're going to do is essentially for all the variables in our little cost matrix, we're going to define a symbol. So V for value, I for incentive cost, C for contact cost, and gamma is this fraction of the churners that is going to accept the incentive. Then we're going to build a cost matrix. So we're going to use this cost matrix class. And step by step, we're going to add the elements of our cost matrix in. So first, we're going to add the true positive benefit of when they accept the incentive. So that's gamma times value minus incentive minus cost. Then we're going to also add what happens when they don't accept, so 1 minus gamma. So those two terms are just added to each other. And then we're also going to see what happens when we made a mistake, when we made a false positive mistake. So we'll add those costs as well. So you can see kind of, because this can quite easily become very complex, I chose for like a builder-style API where we can kind of layer the different pieces all together, and then Empulse knows how to deal with this. And then once you have done that, well, you can take this cost matrix and translate it to different metrics. So maybe one thing before, using these V, I, and C is not very descriptive. So one thing I added to this cost matrix is the ability to alias. So for example, gamma is accept rate, V is value, I is incentive cost, and C is contact cost. So when you refer to these symbols later, you can do that in a way that's actually readable in code. So for example, you can also set default values for some of the things in the cost matrix. Let's say incentive cost is 10 and the contact cost is 1. And then later, when you call something with it, we don't need to repeat those values. So how do we translate that to a different metric? So we use the metric class, and we provide the cost matrix that we have defined earlier. And then we also need to define a strategy. And that strategy, all that it is saying, is just how to interpret the elements of the cost matrix into a metric. And then you just have a function that you can just call, like any other function. You provide your true and your probabilities, and then the values for the parameters of your cost matrix. And then compute it like you normally would. And the easy thing with this is, well, you can use a different metric. Like the savings metric that I talked about, the only thing is you change your strategy, and then you compute it as well, same way. Same thing with costs, different strategy, same API. OK. So the reason why I've chosen for this API is because, well, what is often done in this kind of fields is, well, right now, every parameter of the cost matrix is deterministic. We just say, the incentive cost is 10, right? We don't express that there is any uncertainty. And for some parameters, this might be fine. But for other parameters, like what the fraction is of churners that are actually going to accept, we might not know beforehand what this fraction actually is. So we might want to express that there's some kind of uncertainty there, that this is actually a stochastic variable. And this metric should be able to deal with that. So what we can do, here's just an easy example. Instead of saying gamma is a normal symbol, we say gamma is actually a uniform distribution. But this can be a gamma distribution, can be a beta distribution, can be any distribution that is available in SymPy. And then the rest of the code stays completely the same. But down the hood, Empulse, the metric, knows how to deal with this. It will compute the expected value over the stochastic distribution. And if you were to implement this in code, it's not even all the code that would be necessary. It gets quite complex very quickly. But I hope you appreciate that this API stays very simple because it's just declaring how it looks like, what you need, and not how to compute it. So we have a metric one now. So I've kind of showed you before. So we have defined a cost matrix. We've added all the different elements in there. Then we've translated that into what it costs, what metric that we want, whether that's expected cost, savings, or maximum profit, or any others. And then now we can apply that in different ways. So how can we apply that? Well, very simply, let's take the CS logits, which is logistic regression, which is made cost sensitive. So we define our cost matrix, the strategy we want to use, and then we just pass a loss parameter to our cost sensitive classifier. And that loss parameter will translate that metric into something that that model can optimize inside of its function. Its loss function. So it will know for CS logits how to compute the gradient in regards to the beta coefficients. But you as a user don't really need to worry about it. You just need to pass the metric you just have defined. And then all the other code, instead of passing the false positive cost and false negative cost, you just pass values for the parameters of your cost matrix. This is a bit more complex example. Where actually we're going to do a grid search. So when first have the score, the metric that we have defined, we're going to make that a score, and we're going to use an advanced feature of Scikit-Learn. I don't know if you've ever used that. It's something called metadata routing. But essentially, like I think starting from Scikit-Learn 1.3, this was added, and lets you kind of route different parameters, like in a grid search or in a cross-validation, to the right things in your pipeline. So we're going to say, well, this metric needs an accept rate parameter and a value parameter. So later, when we then do a grid search, we can then pass our model, pass the parameter grids we want to do our grid search over, and then pass the score. And then when we call the fit on the grid search, we can pass the accept rate and the values, and this will properly be routed to this scoring parameter. But you can do something very similar with a model, like a cost-sensitive model, where you just have to call set fit request instead. So I've thrown a lot at you. I know. But there's a lot more out there, so don't worry. But this kind of concluding the talk a little bit. Empulse, there's a bunch of cost-sensitive methods out there, like doing it in different models, evaluating your models in different ways, pre-processing techniques, and so on and so forth. And Empulse really tries to make very high-level abstractions where you just have to focus on defining what your business goal is, and expressing that in a cost matrix and then into a metric. And you don't have to worry about how all of this translates to all the implementation details. You can just worry about, this is what my business needs. Trying to do, Empulse tries to be one-stop shop, so together with Scikit-Learn, you shouldn't really need anything else to do cost-sensitive learning. Of course, like your pipelining and things like that, you need other stuff, but for cost-sensitive learning should be all you need. And this is my first open source project, so I'm really happy if you find it useful and you might think, well, this could be interesting to add to the package, just contribute. I'd love to have people work with me and have some feedback on the things that I'm doing. So you can just, it's one pip install away to try it. The link will take you to the documentation page if you scan the QR codes. Please add me on LinkedIn if you want to have a chat after, or come to me in the break. I'd love to talk as well. And then get up my email address if you want to email me. So yeah, I think in general there's like a bunch of interesting stuff you can do with cost-sensitive learning. It's not always like a free lunch, like for example, like the instance-dependent costs. There's like a lot of trade-offs that I haven't really talked about. But like, if you use like instance-dependent cost in your model loss, it can be like a bit trickier for the model to learn because you have a very hilly loss landscape and so on. But like a lot of those details is also like explained in the documentation if you can have a read through it. But like in this talk, this is the most I could fit in. So thank you so much for listening, and I'll happily take any questions right now.
All right, amazing. Do we have any questions from the audience? Okay,
yeah.
over there.
Hi. Thank you so much for your talk. It's really impressive for your first open source project, especially writing in Python. But I'm a little bit not like anxious, suspicious, but because there's already functionality of defining custom evaluation laws in XGBoost or like GBM.
Yeah.
And have you also like compare with it? And other question, why did you decide to get functionality of model training into your package?
Well, a lot of these, like for example, you mentioned like in XGBoost, you can already define your custom things. A lot of these are just like a user-friendlier interface to that. And down the hood, we're using that capability of defining your custom metric. And when it compares to like, using, for example, the sample weights or other techniques, I found that in situations where you have like very big heterogeneity, where, for example, in a churn case where you have very high value customers, very low value customers, using these cost-sensitive ways are generally outperforming. For things that are not as defined, have not that big of a differences, it's really up to doing some benchmarking. It's not always better, always worse.
Yeah, thank you. Just one little remark.
Yeah.
It's just from machine learning practitioner, it's not like really easy to abandon XGBoost or like GBM and to shift to like new library.
Excuse me, can you repeat?
It's not really easy to shift from one library to another, from XGBoost to Empulse, for example.
Yeah, sure. So your question is that? No, just like. Just a remark. Okay. Yeah, sure. Thank you.
Thanks for the very nice talk. Early on in the presentation, you introduced the different classifiers that are part of Empulse, and you say like, you don't have to worry about how these cost-sensitive things are included in the model training. It's abstracted away. But I'm still interested, maybe on a high level, like how is this used during training? I guess you modify the loss function in some way.
Yeah.
Is effectively assigning weights to the instances based on ground truth, or like how do you modify the loss function with these costs?
Yeah, sure. Well, for like logistic regression, for instance, we just take the equation of the cost loss and just derive that with respect to the beta coefficient, and then use those to do like I think either gradient descent or like LBFGS solver on that. But for example, like for the tree classifiers, you essentially split your tree so that the nodes are as have the lowest cost associated with them once you split them. So you evaluate different splits and then different costs. But I think we better take this conversation offline, because I think if I go into very much detail into explaining
my main question is that the cost itself is not differentiable, because if you cross the threshold, there's
Oh,
discontinuity.
yeah.
So how do you calculate gradients and things like that?
That's an important caveat. In the expected, in the model losses, we use something called expected loss, and not just the cost loss. So you don't have 0-1 predictions, but you have the continuous space of anything in between. I didn't really explain that in the talk, but you also have like these expected cost loss and so on in Empulse that you can define. But yeah, that is differentiable. There are some other things that are not differentiable, like the maximum profit things, but there's like other methods that use like meta-heuristics, like genetic algorithms to optimize the loss and so on. But yeah.
Thanks.
Yeah, that's a very good remark. Thank you.
Hey, thank you for the really good talk. This may be quite a naive question, so I apologize if that's true. But we're looking at the cost, the cost functions when you go from the confusion matrix.
Yeah.
I was looking at it, and obviously, usually with confusion matrices, you've got a classification of true or false.
Mm-hmm.
When we're looking at the cost function, it's a scalar value. So the really, really possibly dumb question is, why is this a classification problem as opposed to a regression problem?
So
it might be a silly question.
Yeah. So I think if I'm understanding you correctly, you're the thing that you're you're still predicting is you're thinking, why not predict the cost itself, and then instead of making a classification problem?
I'm not sure, to be honest, but part of it is when it jumps out as from the confusion matrix space.
Yeah. But well, there's a difference between the actual task that you want to do and classifying someone as churner or not churner, someone as ill or not ill, things like that, and the actual loss that you use or the metric that you use to evaluate it by. So, yeah.
So the loss space is okay. Cool.
Yeah.
Thank you. It was a silly question. Thank you.
Hey.
Thank you for the presentation. I have a question about the cost-benefit matrix, and because I was actually dealing with using cost-benefit matrix for B2C, like kind of like a model. And it was a bit easier for the stakeholders to come up with like what would be basically the values for the cost-benefit matrix. But when it's coming to the B2B sector, it's a bit more difficult, because then like the nature of the customers is really different from each other.
Yeah.
Do you have any recommendation on calculating the cost-benefit matrix for this kind of challenging situation?
Yeah, I have done a project myself, which is also in B2B setting where this was very challenging. I think my experience, the difficulty is never with like using these cost metrics, like cost-sensitive things itself, but rather like defining this cost matrix very well. And that was, I think, for the project that I've done, like a lot of trial and error. I think just talking a lot to the different stakeholders and trying to get a grasp of what the business reality is. But I think that's like, a lot of it is just, it depends. I don't have like general recommendations for it.
Okay. And maybe like a follow-up question on that. So, for example, do you think like the customer lifetime value would be useful for these cost-benefit metrics?
Yeah. Like in the for example, the churn example, I've just said value, but in practice, is like the customer lifetime value that you're using. So yeah, definitely, I think the easiest way of making these cost matrices in a business setting is often of using this idea of value modeling, where you can, like, things like are typically like not very tangible. You can kind of, there's a lot of methods like conjoint analysis and things like that to make them like put some kind of value on there which is quantifiable that you can actually use. And like a lot of, using those kind of methods can really help, and like having a reliable estimates of customer lifetime value and using that in your cost matrices can be very useful. Yeah.
But then is it possible, for example, to use like separate CLVs for different types of customers? For example, like for bigger customers and like smaller companies?
Yeah, absolutely. I think an example I gave here, for example, so you just defined in your cost matrix one value, but you pass an array of different values through there. So in this case, every customer will have a different CLV associated with them, and the metrics will take into that into account, and also the models if you optimize with those.
Yeah, thanks for the great talk. I have a question on incorporating like a time component in the costs. So let's say you have an ill patient, you make a decision whether or not to operate. Then of course, the gain of this doing the operation is also related to how long the patient will benefit from it. Do you have any suggestions on incorporating like time in your benefit analysis?
I think at some point you have to make some kind of simplifications. In essence, you're always kind of modeling reality in a way, and you have to make some kind of trade-offs in between what is reasonable to kind of models and how complex you can get it. A lot of these like time-based stuff is tricky to really get in there, especially if there's a big range. But yeah, I have to think about it because I haven't like faced that problem myself. Yeah. So it's a good question to ask. Thank you.
Yeah, thank you so much. I think that's it for now. Thank you so much for the presentation. We do have a little gift.
Okay.